suppose I've certainly bored you enough in the previous 4 lectures with those eigensystems and such like. We are now moving to something that is perhaps more obviously related to chemistry, and that is the advanced differential equations. First years have seen the elementary physical introduction and their kinetics already. Second and third years would be pretty comfortable with aspects of it by now. But what we'll do here is spend 4 whole lectures on the deeper mathematical aspects of this, on how to solve them, on what they are, on what the classification is, and also a couple of lectures on the applications of differential equations to chemical pharmacokinetics and other such matters. So today's lecture is not actually so much about mathematics as it is about applications of what we are about to learn in chemistry. So I focused it on pharmacokinetics, in particular on the general things and on the 2 things that are highly relevant to you as students, and that is the pharmacokinetics of ethanol and THC, both of which are, have interesting history and interesting features in them. Right, so in general, pharmacokinetics is about the fate of substances in the body that are not intrinsic to the body, so not naturally produced. And normally when they are introduced into the body in some way or another, they are treated as foreign substances. And then, as you know, those of you who do biochemistry modules, there's an army of various detoxification enzymes, mostly oxidases, whose job it is to take the substance you've ingested and make it soluble or to conjugate it with something that is easily eliminated. So normally what would happen is something is ingested through the mouth and goes into stomach and gut. Through the bloodstream, as it's absorbed in the gut, it gets into liver, which is the location where all the detoxification predominantly happens for the ingested substances. Insoluble things are solubilized by oxidation and hydroxylation. Soluble things are conjugated to make them easier to transport. And normally the things end up in the kidney and end up being excreted at the rates that depend on the chemical nature of the substance. So the models, the mathematical models of this process, they make use of the concept of a compartment in the body. And this is our first topic today, compartments. I have reproduced a picture from a large pharmacokinetics textbook in your handout that lists a fairly extensive catalog of compartments. But for something fairly simple, we would say that we've got a digestive tract. And that's one compartment. From there, it will go into blood. From blood, there are multiple locations where it can go: interstitial liquids in tissues, then various things that are more soluble in fat than they are soluble in water would go into adipose tissue, fatty tissue, rather separate from, for example, the muscle tissues in there. Then parts of what goes into blood might end up in the central nervous system if it crosses the blood-brain barrier. Things will end up in kidneys. And out of there they'll get excreted. Or they might end up in the lungs and excreted through gas exchange. But what is important when we start to formalize this picture is that we have a network of compartments with chemical exchange reactions between them. Our substance ends up in the digestive tract, gets into the blood with some rate constant, and perhaps gets back with some rate constant. Out of the blood, some fat-soluble things, like certain fluorinated drugs, will end up dissolved in fat, but also will end up reabsorbed into blood. This is why in certain toxicological conditions it is rather dangerous to fast, because when your fatty tissue is being consumed by the organism, everything that is dissolved in those fats will be released, and it's actually possible to get yourself poisoned if that fatty tissue disappears too quickly. What we are looking at, therefore, is a substance that enters a compartment and is getting exchanged between compartments. So this is a compartment A, compartment B, C, with chemical reactions between them. And these reactions are not actually transformations, they are transport. Plus, 1 minus, that's 2 plus, and minus. And then the concentrations of the substance in each compartment are actually described by the differential equations you are quite used to. If we start writing the system down, dA by dt, so the change in the concentration of our substance in compartment A as a function of time will be proportional to the amount that is A inversely, because it's being consumed, and then with a plus sign to the concentration in compartment B with a plus because it is being replenished. So the usual thing, minus K1 plus A plus K1 minus B. So the more there is in A, the more is removed per unit time. The more there is in B, the more is returned from B per unit time. The usual kinetics. And then dB by dt for different reactions. B is being replenished by K1 plus. It is also being replenished by K2 minus. And so, but that is A and that is C, so we should put a bracket in here. So K1 plus A plus K2 minus C minus two reactions vertically B, K1 minus and K2 plus. And similarly for C, dt. Right, so I think even the first year students have by now seen such reactions using their kinetics. So today is about setting this up more formally as a mathematical framework. And in particular, about looking into more complicated things. So for example, if B is being conjugated to glutathione and then subsequently removed, there will be another reaction that is the concentration of glutathione times the concentration of B times the reaction rate. Right? This will be a second order reaction with certain assumptions, right, about how this proceeds. But this is how such systems are built, and to you, these are networks of chemical reactions that you know more about than I do by now, but to me, these are systems of ordinary differential equations. That is my job to teach you how to solve. Now, all of you can solve basic things like radioactive decay by now, but I will teach you to solve situations where you have multiple equations, where equations are not linear, where you can have things that are continuously added and removed from the system. So, for example, if somebody stands there with a shovel and adds A in a continuous stream into compartment A, you would have an extra term in here. And then if somebody removes it from C at a constant rate, there will be an extra term there. So constructing these things and then subsequently solving them is what chemical modeling is actually about. It's a pharmacokinetic context. Right, so let us go into something practical. An excellent example of how to work with these equations is the pharmacokinetics of ethanol. Now, of course, ethanol as a substance people ingest is as old as mammals themselves. You have all seen that wonderful article on the BBC about a moose in Sweden that got stuck in the apple tree after being wasted on fermented apples and trying to climb it to get some more. So, well, you get the idea, right? My hamster rather enjoys a bottle cup of beer every now and then. So every mammal more or less has the same detoxification mechanism, and ethanol has the same. effect on that. The story begins actually in the early 20th century, 1919, I think, when Edward Mellanby started injecting ethanol into people and then measuring its concentration in the bloodstream as a function of time. He concluded that the elimination of ethanol proceeds at a constant rate, what we would call these days a zero-order reaction. He said, in a person of a certain mass, once ethanol is injected, the rate of elimination doesn't actually depend on the amount injected, and is about 0.15 grams per kilogram body mass per hour. Everybody shrugged their shoulders and said, well done, but then of course chemical kinetics arrived around about 1940s, and as you know, as chemists, zero-order reactions are never elementary. Something must be happening in there that's not just simple consumption of alcohol, and people started to criticize me, saying, okay, this cannot possibly be a zero-order reaction, and this must be wrong, and so on, until about 1959, when the concept of the enzyme appeared. So people realized that proteins are actually chemical machines, and some of them at least that perform chemical transformations. And so the story became a lot more interesting when it was pointed out in 1958 that the reaction must in fact be like this. If we have the enzyme, this is for enzyme, not ethanol, and we have a substrate, then the first thing that must happen is the enzyme must reversibly bind to the substrate. There's a pocket inside alcohol dehydrogenase which would coordinate somehow or absorb the molecule of ethanol. And alcohol dehydrogenase is a zinc-dependent oxidase, NADH, where ethanol is being oxidized into acetic aldehyde. K1 plus and K1 minus in here, and the oxidation is irreversible to a good approximation, so we will have the enzyme that is being returned into the pool of the enzyme, and then the product. Now I'm simplifying here somewhat because there has to be the coenzyme binding stage, and there something has to replenish the coenzyme, and so on, but this is very approximately the picture. And that's the enzyme substrate complex. And so as mathematicians, we're looking at that and thinking, all right, that's a two-stage partially reversible chemical reaction, clearly nonlinear kinetics, and so how on earth was Mellanby able to measure something that actually eventually drops into zero order? So we are tasked here with the mathematical analysis of what's going on. So let's write some differential equations and let us think about what we see. So dE by dt, alcohol dehydrogenase, is being bound into the enzyme substrate complex in the forward reaction, minus K1 plus E times S. It is being replenished in the backward reaction, minus K1 minus in here ES. So somewhere there's a product and somewhere it is just ES. Maybe I should start using square brackets, but so far it's not terribly confusing.
Plus K1.
It should be a plus. And then it is also replenished in the next reaction. Interesting, this won't just only come back this way, it also comes back that way. So plus K2 ES. So that is the reaction for our enzyme. Then ds by dt, so the fate of alcohol, it can be absorbed into the enzyme or it can be desorbed back from the enzyme if the reaction doesn't happen. So it's consumed, then K1 plus E times S, but it's replenished, K1 minus ES. Then the enzyme substrate complex, ES by dt, is similarly replenished by the forward reaction and drained by either the non-reactive debinding or by the chemical reaction. So plus K1 plus E times S minus K1 minus ES, and then minus K2 ES. And then d product by dt is simply just obtained in the second reaction. So plus K2 concentration of ES. So people started looking at, okay, this really doesn't look like a zero-order process, so what on earth is going on? Then, of course, they realized is the concentrations of ethanol that we are ingesting. Consider it typical undergraduate on a typical jester's night. How much do you know? So imagine about quarter a liter of pure ethanol equivalent would not be unreasonable for some individuals. Anyway, the concentration of ethanol vastly exceeds the concentration of detoxification enzymes in your liver, which essentially means that anything in this reaction scheme that could possibly have been an unbound enzyme is in here. So all the enzymes that you have, because of the overwhelming concentration of the substrate that's coming into the system, is bound up in the enzyme. And the moment it reacts and is back, released back, it's instantly rebound by the substrate. And so, because most of the enzyme is sitting in the enzyme substrate complex and the concentration of the enzyme is more or less constant, it's not constitutionally expressed, it's induced. But essentially what this means is that the concentration of this is A, as high as it can get, and B, a constant. The so-called quasi-stationary approximations that the people who have attended first semester of this course have already seen. Anyway, what this means in practice is that the concentration of that ES is actually constant, that this derivative is zero. That is zero. This moves a lot, but the concentration of the enzyme substrate complex is constant. What does that mean? Well, it means that we get one of the equations in this big system of differential equations to become algebraic. So let me rewrite this a little bit. K1 plus E times S equals, I'll shift that and I'll shift that forward to the right hand side. K1 minus plus K2 yes. What use can we make of this? Well, we can actually take this and eliminate ES from there. Or let's perhaps eliminate that. So I will take this entire term, K1 plus ES, so K1 plus ES, and I will simply put that into its place. So what this becomes is minus K1 minus plus K2 ES plus K1 minus S. K1 minus K1 minus cancel. K2 ES. But then, of course, we made the assumption that the concentration of enzyme substrate complex is a constant. And so, minus in here. And so that is some negative constant. And so Mellanby was actually right. D substrate by dt, under the assumption that you have really got yourself knackered, is approximately a zero-order reaction. And this constant, as per Mellanby, is about 0.15 grams per kilogram body weight per hour. So from here you can actually estimate how much drinking you can realistically do. Mellanby was British, and so this is actually the average elimination rate for your typical Brit. It is highly dependent on the geography of your origin. If you come from places like Korea or Japan, your enzymatic system is significantly different. You process ethanol considerably slower. you may have some friends like that who, get really drunk from a tiniest amount. And you probably have friends who vastly exceed this metabolic rate, and they can just drink it to no end. Anyway, so Mellanby endured about 20 years of scathing criticism over his measurements being impossible, not making any sense, and so on. But of course, the only thing he did is simply to measure it as an honestly reasonable findings. I've reproduced a picture from another pharmacology textbook. It merits perhaps a more detailed discussion on what happens once you ingest ethanol. Of course, one complication we have not accounted for here is that it takes time to absorb from your digestive system into your bloodstream. So there's an initial rise and then a fall, and then if you've ingested more of it, and then there's a rise, and there's another fall, and if you've ingested still more of it, then it goes like that. What is very important here is these linear intervals. So that range is when the absorption from the gut into the bloodstream has already happened, and where this entire kinetic model is actually valid. And then at this point, our principal assumption that the concentration of ethanol overwhelms the detoxification system is broken, and so we are back to nonlinear kinetics and it fades. So in here, it's actually 0, 0, whatever. And our job in this course, the next 3 lectures, is about how do we solve these actual differential equations and obtain these things analytically or numerically. It turns out, so long as the equations are linear or roughly linear with few nonlinearities, they're easy to solve. As soon as equations are non-linear, the only way to really solve them is numerical. So this brings us to the next topic, and that is the pharmacokinetics of tetrahydrocannabinol, where I will already sketch the way of solving such systems of equations, and also find a new use for eigenvalues and eigenvectors that we have covered in the previous lectures. Okay. Item 3 on the agenda is THC and a different mathematical story about pharmacokinetic differential equations. Tetrahydrocannabinol is rather large. I've got the structure in your handout. I will not redraw it on the board. I will simply get the relevant bit of it. It's this metal group on the very top. This is what gets oxidized. If you look at THC itself, you will see that it's not terribly polar. There's an OH group hanging out and an oxygen in the heterocycle, but something like this, particularly given the long fatty acid, fatty perhaps, simply just aliphatic chain hanging from the side and an aromatic ring. This is likely, and it actually is, A, an oil, and B, it is soluble in non-polar liquids, like acetone and fat and so on. So the body's principal mission when it detects tetrahydrocannabinol is to make it soluble, because then it can be excreted by kidneys. And the best way to make it soluble is to pick a convenient metal group and start oxidizing it. So the first thing that happens to THC, when it goes into the body with the time scale of about 1 hour and irreversibly, 1 hour, it is oxidized from a metal group into SCH2OH. Now this substance is psychoactive. This OH substance has an interesting feature. It is both psychoactive, but it is also antipsychotic. That is, it gives you the euphoria, but it also suppresses the various nasty psychiatric side effects. So the thing is sort of self-regulating. And that happens in a matter of about hours. So you've got these two substances in your bloodstream. The interesting thing happens next. On the time scale of 1 week, that gets transformed into the next substance, and that is wait, no, this is an hour. One hour. The next logical thing happens is this becomes a carboxylic acid. And then, of course, this is highly soluble because it can become ionized. As soon as it's highly soluble, it gets filtered out in the kidneys because it's a small molecule, and it's simply getting excreted. Good thing. Except there's a little problem in here. The excretion timescale is of the order of a week. These two substances are psychoactive. This substance is not psychoactive. And it sits in your bloodstream for weeks. So you've ingested a little bit of THC, you got your psychoactive period of the matter of hours from this and this. Then it got oxidized into the carboxylic acid, and the time scale of elimination of the carboxylic acid out of your system is in the weeks. That is to say, this carboxylic acid can be detected in your system. If half elimination is a week, some traces of it will be sitting in your system for months. And so the people who are running the mass spectroscopy facilities at Heathrow Airport no longer even pay attention to the detection of this substance because half the passengers have it in them because they don't realize that the traces are persisting in their system for such a long time. But it's true. Anyway, our job, of course, is to write a bunch of differential equations about it and look at what happens. Let's call this substance A. Let's call this substance B. And then that substance will be C. dA by dt is just the consumption in the forward reaction. Let's call this A minus A1A. Then A goes into B, so dB by dt is whatever arrives from A plus A1A, and then whatever departs into C minus A2C. And then dC by dt is whatever arrives from C, from B. So that should not be it. dB by dt should be B. And then dC by dt is whatever arrives from B minus whatever departs out of the system. So that reaction is our K2 and that reaction is our K3. I will give you a formal proof of this statement in the following lectures, but for now I can tell you that when we are asking ourselves what are the characteristic timescales in these reactions, timescales are eigenvalues of the kinetic matrix. If we rewrite this in the matrix vector form, which we will do in a moment, what will then happen is we will have d vector of concentrations by dt is the kinetic matrix times the vector of concentrations. And then the general solution to this, so solution is always the following form. Let's say A of t will be alpha e minus lambda 1 t plus beta e minus lambda 2 t plus gamma e minus lambda 3 t and so on, where alpha, beta, and gamma are constants that depend on initial conditions, but lambdas are the eigenvalues of K. Which we will now go and compute. So actually all of the boring algebra that I gave you in the first 4 lectures had a reason. When you are dealing with chained linear chemical reactions, you will actually have to calculate these eigenvalues because they have the physical meaning of the time scales of your reaction system. In this case, actually, the time scales are fairly straightforward, and you can probably already see what they are. Like we should have a couple of time scales which are in the hours, and a time scale which is in the weeks. But when you have more complicated networks of branched reactions, some time scales might be very limited because certain substances might persist in the system way less or way longer than the kinetic reaction scheme might suggest because of some complicated interference of chemical processes. So let us do 2 things. Let us rewrite this system of differential equations in the matrix vector form. We know how to do it. And then let us calculate its eigenvalues and actually convince ourselves that the eigenvalues we will get will correspond to the characteristic types of the reactions that we have specified over there. Alright, so d by dt of our vector of concentrations A, B, and C. So we have a vector space, however it has no geometric meaning because it is a vector of concentrations, but it is just another 3-dimensional space. It's R3, and we can set up scalar products and other things, geometry, notion of distance, and so on, except in this case this would be distance in some abstract coordinate space, concentration space. Okay, dA, dB, and dC should be a matrix here, and then A, B, and C. What do we have? dA by dt is minus K1A, so whatever's in the matrix must be multiplying just A and not multiplying either B or C here. The way we multiply matrix by a vector is to take it and multiply it into a row, so there must be minus K1 here, 0 here, and 0 here. Then dB by dt is K1A minus K2B, so plus K1 minus K2, and C does not occur, therefore it must be multiplied by 0. And then finally dC by dt is K2B minus K3C, A does not occur, plus K2 minus K3. This is our kinetic matrix, and let us now calculate its eigenvalues. This is K. What we want to know is which vectors and which numbers satisfy the following relation. Where K is our matrix, B is some vector, and lambda is some number. The chemical meaning of this is fairly abstract. By now, we are asking what are such combinations of concentrations that our kinetic matrix doesn't rebalance, just simply fades. So what are the concentration combinations that are in some sense stationary in the system? And the way to do it is to notice, as we did in the previous lecture, that's a matrix, but that is a vector, so we put a unit matrix into here, because it doesn't do anything to a vector, but it allows that to be subtracted. So I move that side over to the left. So K minus unit matrix times a lambda times B must be 0. As you know, such systems, when they have unique solutions, will necessarily have a 0 solution. So we must demand the determinant of this be 0. So determinant of K minus unit matrix times lambda is 0. We write that determinant, so that of that matrix there minus this, and lambda 1 is just lambda, 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 and the rest of the elements are 0. So the unit matrix multiplied by lambda. So what we have it here is minus k1 minus lambda 0, 0, plus k1, and then minus k2 minus lambda 0, 0, plus k2 minus k3 minus lambda, and this determinant must be 0. Let us calculate it. Remember that geometric schematics that I gave to you. This product, that triangle is 0, that triangle is 0, so with the plus we only have minus k1 minus lambda, minus k2 minus lambda, minus k3 minus lambda, and with the minus, counter diagonal product 0, this triangle 0, that triangle 0, so thankfully the determinant here is actually quite simple, it's just this. And from here the solutions are immediately obvious. We have lambda 1 equals minus k1, lambda 2 equals minus k2, and lambda 3 equals minus k3. So the time scales of our dynamics in the system are actually exactly the time scales of the three chemical reactions. This is because we don't have anything that is reversible, we don't have anything that loops back on itself, we don't have any multiple paths into the same system. This is when the complications appear in this matrix, and this is when these eigenvalues will stop being so simple. But as you can see, and perhaps this is a valuable connection from the utterly abstract formalism that we have here into the more realistic chemistry that I have presented there, that all the formal mathematics that I've been torturing you with is actually coming from real practical chemical problems. Okay, so one next thing that would be necessary if we were to solve this problem fully is, of course, to substitute these three individual eigenvalues into there, get the corresponding eigenvectors, normalize them, and that's unfortunately even here in this simple reaction system is a bit of a mess, and so I will skip that. I've got I think that is delegated to lecture 4 on this subject, where we will finally obtain them and look at them. But for now, I will mention two things. First, I will just reproduce the thoughts and do a bit of discussion as to what they mean. So the moment tetrahydrocannabinol is ingested, of course, it is rapidly, in a matter of hours, converted into THCOH, but the original substance A is simply decaying exponentially. Our A, just because this differential equation here doesn't actually depend on what happens subsequently, and so the solution to this is just a pure exponential decay. As A is being consumed, of course, B is being replenished, so proportionally, and so you have the metabolite, the first metabolite of it rising, and eventually it is also being consumed. Then the metabolite C has an interesting fate in that it is produced as B is being consumed, and there is initially no B. So it starts off rather slowly, but then also rises as B is being consumed, and reaches approximately the level of the initial concentration of our substance A. And finally, as both A and B are consumed, it reaches the peak that corresponds more or less to the initial concentration. And then, because the elimination of C is so slow, it goes and goes and goes and goes. So the time scale of this is days. This process is fairly rapid in here, so you are detoxed to the point where your central nervous system is able to regain its normal functioning in a matter of hours. And this is, of course, from the point of view of evolution, is essential. Imagine that you're an animal somewhere in Afghanistan just eating the wrong kind of plant. And, well, getting incapacitated as a result. Mother Nature better make sure that you are recapacitated quickly because you've got to run away from something scary. And that does actually happen. However, what Mother Nature is rather less concerned about is whether anything lingers in your bloodstream later, particularly if it's not particularly toxic. So, through the evolutionary history of the animals that had to deal with that, including ourselves, excretion of the metabolic product has not been a high priority. Accordingly, evolution didn't optimize it for expression, and it's actually sitting in the system. And that's the kind of modeling that you have to do to fully understand it. Now, in practice, as you know, we rather rarely do it analytically. We do it with computers. And I will sketch the way that computers do it. Imagine that system in here being given to a computer. As you know, the definition of a derivative is a limit. So df of dt is limit delta t going to 0 of f of t plus delta t minus of t divided by delta t. The standard definition of the derivatives that you have covered at school and we have covered at the university in some detail. You must have seen this somewhere before. Approximately, however, if we put delta t to a sufficiently small number, we needn't take the limit. We can say to a pretty good accuracy, it's like this. And so imagine we're doing this here. So our c delta of t plus delta t minus c delta of t divided by delta t is approximately equal, the more accurate the smaller this time step is, to kc of t. Well, we can solve this for c of t plus delta t, so I will multiply it by delta t, and I will shift the concentration over there. So c of t plus delta t is k, let's say c of t, this term, plus delta t times k times c of t. Notice what we have here. The concentrations at the next time point, t plus delta t, are related by a simple algebraic equation to the concentrations at the previous time point. And so the computer simply needs to choose a small enough delta t. It knows what the concentration was at this point because that's the starting condition. When the time slice delta t is sufficiently small, this approximation is really good. So the computer is able to calculate the concentrations at the next time point from just arithmetic and a matrix vector product. So it knows the concentrations here. As soon as it knows the concentrations there, it resubstitutes it into this equation and obtains the concentrations at the next point. And so on. So again, those who have been at the semester 1 course know that this is called Euler's method. But I only gave it to you for scalar quantities, and now you can see it's actually extended to vector quantities, but it's exactly the same algorithm. And this is typically how we are doing the pharmacokinetic modeling, and this is where your pictures in the handout are coming from. A machine algebra system called Mathematica has done all of that, interpolated the point and plotted the graph for your handout. Okay, so the summary for today is, I guess, this entire lecture is a colossal apology for what I am going to teach you in the next 3 lectures, which will be rather nasty differential equations and their systems and so on. I thought I'll just give you the reasons why I'm doing that to you before I do that to you, otherwise you will all disappear and pick another module. So toxicology and pharmacokinetics is all about tracing substances in the body. There are various compartment models that when you start thinking about them leads to systems of ordinary differential equations. If you are really clever about it and you want diffusion in these systems, there will be partial differential equations, which we'll get to. The two famous examples, one is ethanol, and why Mellanby was right after all, after years of development in chemical kinetics, finally it turns out that he was actually completely correct. And empirically measuring constant elimination rate. And then there's a very interesting story of tetrahydrocannabinol and how it leads to a system of three differential equations, and then the eigenvalues of the corresponding matrices are in fact the elimination timescales for the three substances from your system. Okay, so the next three lectures are about the mathematical nitty-gritty of how we solve such differential equations, and you will have plenty of practice in the workshops.